epoxide opening under basic conditions. And so epoxides are these little 3-membered ring ethers that are a lot more reactive than normal ethers. Typically ethers are not reactive. We do see they cleave with strong acid, but that's about it. Epoxides are an exception to that because there's a lot of ring strain by forcing these atoms into this 3-membered ring. And so we can do reactions that add nucleophiles to epoxides, and they open up those epoxides either under acidic conditions or under basic conditions. And so in this reaction, we're going to take a look at basic conditions. And so I am going to draw an epoxide. So here is an epoxide, and I want to make sure this is not symmetrical, so I'm going to add an alkyl group here. Because we're going to have to distinguish where our nucleophile attacks, if it's going to attack at the more substituted carbon or at the less substituted carbon. And under basic conditions, the nucleophile attacks at the less substituted carbon center. So it will attack at the less substituted center. Okay, and so we could see something along the lines of a first step, and this could be where our basic nucleophile is attacking. So we could use something like methoxide. And then in a second step, we are going to want to add in some kind of proton source just to neutralize this reaction. So we're going to add just a little bit of aqueous acid as a workup step. Okay. And so the first step is where the nucleophile is going to attack at that less substituted center. And so we know we're under basic conditions because we see our anionic nucleophile. So whenever we see a reagent where we see an alkali metal as a salt, we should recognize, so we typically see sodium and potassium. So this is sodium. So we need to recognize that this is sodium plus, and whatever that sodium is attached to is negatively charged. So that's how we know that we have that negatively charged methoxide. And so methoxide is a conjugate base of methanol, which is a really weak acid. So this is a decently strong base. Okay, so definitely under basic conditions. And this is going to attack the less substituted carbon atom of this epoxide. And so that is going to be this bottom carbon atom right here. And so this is going to attack, and it's an SN2 attack. So if this bond here is a wedge, that means that this is approaching from behind the plane. So when we draw the product, this new bond is going to be on a dashed line to indicate that it came from behind the plane of the paper. So there it is. And we broke this bond, right? This chiral center didn't change. We didn't have a reaction take place there. So there's no reason for those to change. So it doesn't. Okay. This bottom chirality center did flip, but not the top one because it was not attacked. Okay. And so we get to this intermediate, and then in a second step, we can add aqueous acid so that we can neutralize this and put a proton back onto that oxygen. So can draw some aqueous acid, and this will attack and take a proton. And so we will end up with the following product. So again, that top chirality center that wasn't involved, that chirality doesn't change. The chirality where the attack occurred will invert because that is an SN2 reaction. So if you're drawing your mechanism and following your arrows, you should be able to catch where that chirality changes. So the chirality of the carbon that the nucleophile attacked so the chirality of that carbon will invert. So you want to be careful. You don't invert this top center because no reaction occurred just here where we had that SN2 attack.